Okay, hey everybody. So this is the supplement on sequences, section 11.1. And this is going to be a discussion on just a little bit on more precise definitions of the limits that we talked about, a little more on monotone sequence convergence theorem, and seeing how proof by induction plays into those types of proofs. Okay, so in class, we discussed that the only kind of sensible limit in a sequence is the limit as n goes to infinity. So if we say that an goes to L, a real number, more precisely what we mean is this following statement. For all epsilon bigger than 0, there exists a natural number n such that if little n is bigger than that natural number n, then the absolute difference between our sequence value and the limit L is less than epsilon at all points farther out in the sequence. So one way to kind of envision this is if you have your sequence plotted here where we have different values for n, and maybe different outputs. And the idea is that if we have a hypothetical limit L, let's say it's this value here, we can imagine kind of a corridor, so to speak, around L of size epsilon. So one on top and one on the bottom. So everything inside this corridor is within epsilon of L. And our argument is that we can find a capital N. So maybe it's like here, such that when little n is bigger than capital N, our sequence stays in this corridor. Now this capital N will depend on epsilon. Usually if you pick a smaller value for epsilon, you'll have to pick a larger value for capital N. You'll have to go further out in the sequence in order to ensure that it stays within that corridor forever. But this is more precisely what we mean by the limit an goes to L. The limit an goes to infinity means for all m bigger than 0, so you pick some positive number, there exists a natural number n such that if n is bigger than n, such that if we go far enough out in the sequence, then an will be bigger than m. So note that this doesn't just mean that an at some point will get bigger than m, but it also has to stay bigger than m for all points after that. So really what we're saying here is we have a scenario. Let's think of this as maybe 0, and here is our n axis, and we have our inputs with some outputs. And the idea is that if you tell me an m that you're interested in, if my claim is that an goes to infinity, I should be able to give you, say, a capital N, maybe it would be here, such that all the outputs from that point forward stay above m. So I wouldn't be able to give you an n, say, here, because this one does go above capital M, but then we drop back down. But at this point, maybe we suppose that all of the outputs from this point on are larger than capital M. So this n would not work, but this n would. And this n that we choose, the capital N, is usually going to depend on m. So typically, the larger the m is, the more we're asking for, the further out in the sequence we're going to have to go before we can meet that criterion. So again, this is just to give you a little bit of context for what the precise underlying definitions of these limits are. Okay, so moving on to monotone sequence convergence theorem. Recall that a sequence is monotone if it satisfies any of these 4 properties. And recall that the monotone sequence convergence theorem is a pretty simple statement. All bounded monotone sequences converge. So our first example here is kind of a trivial application, but still kind of an interesting application. So consider the sequence 0, 0.1, 0.12, 0.123. So where each next element, we just glob on the next natural number onto the end of the decimal progression. So you can see, this might be what would it be? A14 would look like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, etc. So an interesting thing about this sequence is that it is increasing because each time we go out, or I guess, so it will be strictly increasing each time that we go out one element further in the sequence. We're adding on some positive amount. It gets to be a very small amount that we're adding on, but we're still adding on some positive amount. Note that it's also bounded. For instance, it's bounded below by 0. And really the important bound is that it's bounded above by, say, 1, or bounded above by 0.2, or we just need some upper bound for it, and we found an upper bound at 1. So by monotone sequence convergence theorem, we can say that this sequence converges to a limit, to a real number. The number that it converges to is called the Champernowne constant, and it has some kind of interesting properties. This has a little bit of the feeling of the kind of monkeys typing on a typewriter kind of problem, if you've ever heard that example. That if a monkey typed on a typewriter just smashing the buttons kind of forever, they would eventually write out the whole works of Shakespeare or something like that. It's kind of this kind of has that similar kind of feel. Okay, so example 2, let's look at this sequence, n plus 2 over n. And we'll start this, of course, at n equals 1. So this is like 1 plus 2 over 1, or 3. And then 2 plus 2 over 3 is 2 2/3. And, 2 plus 2 over 2 is also 3. And then 3 plus 2 over 3 is 3 2/3. 4 plus 2 over 4 is 4.5, and so on. So here we can ask, is this monotone? And it will be after a certain point, right? So what is our sequence? It's for n equals 1, 1 plus 2 over 1 is 3. For n equals 2, 2 plus 2 over 2 is 3. For n equals 3, we have 3 plus 2/3, 3 2/3. For n equals 4, we have 4.5, and so on. So we're strictly increasing most of the time, and we're non-decreasing for this first bit here. So we can see that it's monotone. So is it bounded? Well, it's bounded below by 3, but we can pretty clearly see it's not bounded above. In other words, I think that an goes to infinity. What precisely do I mean by that? Well, if we look back up here, that means that if somebody picks a positive number m, I should be able to find a number capital N such that all elements in the sequence after that point are greater than M. So I could say maybe given M, consider n equals, I suppose we could do n equals M, but let's do n equals M plus 1 just to give ourselves a little buffer. So A sub n, so for n bigger than capital N, A sub n is n plus 2 over n. This is going to be bigger than capital N, which is M plus 1, which is bigger than M. So I could choose capital N equals capital M plus 1, given my capital M, and my sequence is going to be bigger than M from that point forward. So this does indeed show that AN goes to infinity. It does not converge to a real number limit, and that's what I expect from this argument. And we also see that this not being bounded above, even though it is monotone, and even though it is bounded below, not being bounded above does break that monotone sequence convergence theorem. Maybe I shouldn't say it doesn't break the theorem, but it invalidates the assumption, so we can't apply the conclusion. Okay, let's look at example 3. So one kind of interesting, there are some interesting algebraic structures like continued fractions and things like this that are, maybe you would call it like a continued radical or something. It's a whole interesting area of math. And the idea here is that we have square root of 2 plus square root of 2 plus square root of 2 plus forever. And we might be interested to know what happens to this as I put in more and more and more square root of 2 pluses inside of other square root of 2 pluses. Do I think this approaches a limit? If it does approach a limit, do I have an idea what the limit is? So let's try to figure this out. So what's the first thing I need to do is I need to kind of disentangle what this actually means. I can't really start from the inside and work my way out because it's the inside that's kind of going on forever. But what I might notice is that if this is, let's call it X, if I look at this inner square root, this should be just the same thing. This should also be X. Because I'm just, again, doing square root of 2 plus square root of 2 plus, etc. forever. So I should have something like what? Square root of 2 plus X equals X kind of idea. So what do we mean by this? How can we define this a little bit more precisely? Let's define a sequence where maybe our first element is square root of 2. Our next element is square root of 2 plus root 2. Our next element is root 2 plus the previous element. And so on. So maybe I want to define a sequence where A1 is root 2 and AN plus 1 is what? Root of 2 plus AN, and that's for N bigger than or equal to 1. So if I define my sequence recursively like this, I have an algebraic structure I can work with. And I think when this sequence goes to limit L, if it does indeed converge to a real number limit, I think this L is going to be kind of what I'm representing there, right? This would be the formal way to outline exactly what I mean by this kind of a structure. Okay, so what can I do here? Well, maybe I'll try to prove convergence indirectly, and then make an argument based on the recursion of what I think the limit ought to be. So let's first prove convergence. We're going to first prove that the thing does converge. So I'd like to use the monotone sequence convergence theorem here. This does have a feeling that if I take a number, I add 2 to it, and then I square root, maybe that should be increasing. So let's prove a claim that it's increasing. And I kind of mentioned this before, but I'm not going to be super careful with increasing versus non-decreasing. I typically just call them increasing. And bounded. Okay. So let's make a more precise statement of this claim. Let's say that the claim P sub n, proposition n, is that a sub n plus 1 bigger than or equal to an, and that a n plus 1 is less than or equal to 3 and bigger than or equal to 0. So this is our proposition, and this is for natural numbers n. So how can we prove this? Well, when we see that we have a statement that we want to prove for natural numbers, one method of attack is to use induction. So you might have seen inductive arguments before, you might not have seen them before, but in case you haven't seen them before, we're going to go through just kind of a quick rundown of the idea of an inductive argument. So the idea is if I have some claim, Pn, that I claim holds for, let's say, all natural numbers n, I want to do 2 things as part of my argument. I want to start with a base case. I want to prove P1, or maybe P0, or sometimes it might be like P7 or something that I start at, but I want to prove a base case. And then second, I have an inductive step. For the inductive step, I say if Pn is true, prove Pn plus 1. Now, what does this let me do? This, so I have Pn for natural numbers n. So I have P1, P2, P3, P4, and so on, that I initially don't know the truth value of. My base case proves P1. And then my inductive step says if Pn is true, then Pn plus 1 is true. So I could say, okay, well then I could put in n equals 1 there, and if P1 is true, then P2 is true. But now I know P2 is true. So I could plug in n equals 2 into the inductive step, and if P2 is true, then P3 must be true. Plugging in n equals 3, if P3 is true, P4 must be true. And so on. So this proves all of my PNs. The base case is very important because it gives me something to get started with. And the inductive step really does kind of the heavy lifting. It allows me to kind of chain together all of these proofs. I proved one in the base case. that let me show that 2 is true. The truth of P2 shows me that P3 is true. The truth of P3 shows me P4 is true, and so on. So that's the basic idea of induction. So let's start with our base case, and let's call it P1. I think I probably want to call this n plus 1, Pn plus 1. And an n union 0. So maybe not. There. So let's take a look at P1. Is it true that A2 bigger than or equal to A1 and A1 is between 0 and 3? So I can see that A2 is square root of 2 plus square root of 2. I know that the square root is an increasing function, and I have the square root of 2 plus something. So I'm plugging in a bigger input than before. So I get a bigger output. So I do see that just by direct observation that A2 is bigger than or equal to A1. I do see that A1, the square root of 2, that's a positive number, and it's less than or equal to 3. So this is also true. So P1 is true. So typically the base case is fairly straightforward, and the challenge is the inductive case. So the inductive step. Given Pn, show that Pn plus 1 is true. Okay, so what can I say here? Let's look at Pn plus 1. So first I want to know, is An plus 1 bigger than or equal to An? So if An plus 1 is bigger than or equal to An, that's equivalent to saying that An plus 1, where was my definition up here? An plus 1 is defined as root of 2 plus An. And An is defined as bigger than or equal to, and An is defined as root 2 plus A n minus 1. We can square both sides. We don't change the sign. Everything is positive here. We can subtract 2 off of both sides. That doesn't change the sign. So we say that An plus 1 is bigger than or equal to An if and only if An is bigger than or equal to An minus 1. But note that An being bigger than or equal to An minus 1, that's just part of Pn. And we're given Pn, we're assuming Pn. So this is true under Pn. So this is true, therefore this must be true. So we do see that we are increasing or non-decreasing. Now we have to show that we are non-negative and bounded above by 3. So An plus 1 bigger than or equal to 0 if and only if root 2 plus an bigger or equal to 0. But we can square both sides if and only if 2 plus an bigger or equal to 0. And of course, this means that if and only if an bigger or equal to -2, which of course it is, because Pn includes that an is bigger or equal to 0, so it's of course bigger or equal to -2. So an plus 1 is indeed bigger or equal to 0. And we also want to show the other part of the bound, the really important part, that it's bounded above. So again, an plus 1 is just root 2 plus an. This is true if I square both sides, if and only if 2 plus an less than or equal to 9, which is true if and only if an less than or equal to 7. And of course, by Pn, we have that an is less than or equal to 3, which is of course less than 7. So this is also true by Pn. So we have shown Pn plus 1 when we can assume Pn. We've also shown a base case, P1. So P1 is true, but that implies that P2 is true by the inductive step. P2 is true, that implies P3 is true by the inductive step, and so on. So what have we proven here? What we've proven is that an is monotone, and that it's increasing or non-decreasing, and bounded, because it's stuck between 0 and 3. So our monotone sequence convergence theorem says that an goes to a limit that is a real number. We've proven that a limit exists. Now, what is the limit? Can we find the limit now that we've proven it exists? What is L? Well, this is where that corridor idea comes into play, right? If I have a limit L, my sequence has to keep getting closer and closer and closer to it. And in particular, it has to keep getting closer and closer, and then like not start deviating away again. So if this was like a sinusoidal where sometimes it would get really close, but then you could always go a little further out and get far away again, that's not what we mean by convergence. It has to get close and stay close after some point. Or really what I see, I have a relation here that root 2 plus x equals x, or just coming right from this recursive relationship here. So if I'm at my limit, if I'm at L, it ought to be true that root 2 plus L equals L. So this is the key idea, or the second key idea here. We showed a limit exists, and then we're saying, okay, given that a limit exists, given that it has this kind of behavior, that it kind of narrows in toward a limit L, a real number, given that it behaves like that, this must be true, that this recursive relationship has to hold for the limit as well. But this is just an algebraic equation for L. So I get 2 plus L equals L squared, or L squared minus L minus 2 is 0. And this gives me L equals what? Negative b over 2a. So 1 over 2, and then plus or minus root b squared minus 4 times 1 times 2 and flip that sign. So we get 1 plus or minus root 9 over 2, 1 plus or minus 3 over 2. This tells me that L is either 1 minus 3 over 2, negative 1, or 1 plus 3 over 2, 4 over 2 is 2. Clearly, all of our A's are positive. That's what we showed here. So we surely cannot approach a negative limit. So we have to have that L equals 2. Okay. We used the monotone sequence convergence theorem and induction to prove that a limit existed. Then we said, given that we know the limit exists, this behavior implies that we have to have this relationship. And then we can use algebra to find the actual limit. You might ask yourself, well, did we really, most of the difficulty of this problem was going through this whole inductive proof and using the monotone sequence convergence theorem. Do we really need to do that? Why couldn't I just jump into finding the limit right away and be done in a couple of lines of algebra rather than going through all of this? So here's where example 4 comes into play. Let's consider a similar type of problem where we have a recursively defined sequence, a1 equals 1, an plus 1 equals 2an. So we might be tempted to say, okay, we'll take the recursive part. If I have a limit L, then I have to have L equals 2L. Well, that says that I have a limit that exists and is equal to 0. Do I think there's a problem here? Well, what does my sequence look like? A1 is 1. The next one is twice the previous one. So A2 is 2. A3 is 4. 8. And so on. We can pretty clearly see that an goes to infinity, right? So that's no good. We have to prove that the limit exists first. This step in blue up here is heavily reliant on the fact that we have this kind of, corridor understanding of the limit, that we have this understanding that if the limit exists and is a real number, we go far enough out in the sequence and we stick within a very tight corridor around the limit. And that corridor shrinks and can shrink and shrink and shrink as we get further out. So that's a very important thing to know, is that we need to know the limit exists in the real numbers first, and then we can proceed with this kind of an argument. We can't just jump right to that argument off the bat. We need to know the limit exists first before we use that kind of an analysis. And you could even look at a similar, say, example, a1 equals -1 and an plus 1 equals, I don't know, -2an, something like that. So we have -1 plus 2, -4 plus 8, and so on. And here the limit doesn't even exist. It's not plus infinity or minus infinity, it just keeps bouncing around. Or we could have an plus 1 even just equal -1, or -1an, just bouncing back and forth, -1 plus 1, -1 plus 1, and so on, right? So you could think of all kinds of examples of situations where you don't have a limit existing, and if you were to try to just apply this algebraic technique right off the bat, that would lead you to a false conclusion. So we need to first make sure the limit exists, and then if the limit exists, we could, when we have a recursive definition like this, we could maybe leverage that recursive nature to figure out what exactly the limit is after we've proven that it exists. Okay. Okay, so for our last problem, our last example, we're going to look at the Fibonacci sequence. starting with 1, 1, and then each successive term in the Fibonacci sequence is the sum of the previous two. So 1, 1, 2, 3, 5, etc. And we're going to consider AN, which is the ratio of consecutive Fibonacci numbers. So the next Fibonacci number over the current one. And we want to show a couple of things here. We want to show that AN has this relation. We want to show that AN is bounded. And then we'll assume that AN converges and we'll find its limit. Proving that AN converges would be a little more tedious and difficult. So we're not going to actually prove that it converges, but we'll assume it converges, and it does. And we'll find its limit given that it converges. Okay, so let's start with part A. So AN plus 1. So AN is Fn plus 1 over Fn. So AN plus 1 is Fn plus 2 over Fn plus 1. And I know that I want to end up with a 1 here. So I want an Fn plus 1 on the top. So that kind of clues me in. I want to use this recursive nature. Fn plus 2 is Fn plus 1 plus Fn. I can break this into two fractions. This bit is just 1. And Fn over Fn plus 1 is 1 over Fn plus 1 over Fn, or that's 1 over An. So we have An plus 1 is 1 over An. That was what we wanted to show. That's part A. Part B, let's show that this is bounded by 1 and 2. So that gives us kind of an idea of where the limit might be if it existed. So what's our claim? That An is between 1 and 2. So let's check this. Let's say that Pn is that An is between 1 and 2, and let's check P1. So what is A1? A1 is going to be F2 over F1. That's equal to 1. And then that is in the closed interval 1 to 2. So we see that P1, proposition 1, is true. So we have a base case. And now we're going to use induction. So what do we have next? We want to say if Pn is true, show Pn plus 1 is true. So what's Pn plus 1? Pn plus 1 is a claim about An plus 1. But I know I can relate An plus 1 back to An through this recursive nature. It's 1 plus 1 over An. Pn is true means that An is in closed 1 to 2. So in particular, An is positive. 1 over An is positive. So this is 1 plus a positive number. So An plus 1 has to be bigger than or equal to 1 because we're doing 1 plus positive number. Okay, can we show that An plus 1 is less than 2 as well? Let's try to do that. So I note that An is between 1 and 2. So An plus 1, this is less than or equal to 2. So I've got that already. this statement is true if and only if 1 over an is less than or equal to 1, just subtracting a 1 off of both sides. I can multiply through by an. I know that an is positive, so that doesn't change the sign. This is true if and only if an bigger than or equal to 1. And indeed, an is bigger than or equal to 1. This is true. So an plus 1 is bigger than or equal to 1, which we showed. And we just showed now that it is indeed less than or equal to 2. So we can claim now for all n an is bounded between 1 and 2. So we would expect our limit to be some, if it existed, to be some real number between 1 and 2. And then lastly, we want to show that assuming an converges, that there's a limit that's a real number, find the limit. So we're going to assume that here again, because it's a little bit beyond the scope of our discussion to prove that carefully. But I can say if the sequence an converges, let's say converges to L and R, then it must be true that the limit respects this recursion relation. It must be true that L equals 1 plus 1 over L, or that L squared equals L plus 1, or that L squared minus L minus 1 equals 0. So then L has to be negative b over 2a, and then plus or minus root b squared minus 4a times c changes the sign. So this was 1 plus or minus root 5 over 2. 1 minus root 5 over 2, that would give me a negative number. So let's go 1 plus root 5 over 2 or 1 minus root 5 over 2. We know that that can't be the answer. So 1 plus root 5 over 2 has to be the answer. Or this is phi, the famous golden ratio. So kind of interesting little tidbit about Fibonacci numbers is that the ratio of Fibonacci numbers approaches the golden ratio as you get farther and farther out in the Fibonacci sequence. And this is, I think, something like 1.69 or so. So it is between 1 and 2, as we would expect. Okay, so that was what I had for today on sequences. Check back for the supplement on some applications of series, on applications of geometric and harmonic series, but that wraps up sequences.